Hi, I'm Jan. I work as a PhD student at the Zurich University of Applied Sciences. And today my talk is about the paper that we wrote called A Methodology for Creating Question Answering Corpora Using Inverse Data Notation, or How to Generate Data Quickly. Before we look at the actual work itself, let's first acknowledge the people involved in it. This project is a collaboration between two EU projects, the Lilith project and the iNote project. There were three universities involved in it. The University of the Basque Country, the National Distance Education University in Madrid, and of course ourselves, the Zurich University of Applied Sciences. Now that we know who did the work, let's look at the actual work itself. For this, let's consider this example. Assume that we have a CEO of a very important company, and he wants to know which of our customers gives us the most revenue. For this, he just writes down his SQL query, deploys it against the database, and the result comes back. However, this process isn't realistic because you cannot really assume that any CEO is able to just write down SQL queries. So the more realistic scenario is the following, where you still have the CEO of your very important company. However, they hire some database expert who really knows how to write SQL queries. So what happens is that the CEO writes him an email or calls him asking which of our customers give the most revenue. So the database expert then writes down the SQL query, the database returns the result, and then the database expert can forward this result to his boss. The problem here is that this process is quite inefficient because we have a human in the loop, and for more complex queries, what could happen is that you have a lot of back and forth between the database expert and the CEO until the query is correctly formulated. So since this process is a bit inefficient, the vision that we have is to replace the database expert in this scenario with an artificial intelligence. And this artificial intelligence should serve as an interface between the natural language and the database, some sort of translator between natural language and the SQL queries. So then the CEO can just ask the question directly to the artificial intelligence. The artificial intelligence somehow translates it to SQL, deploys it against the database, and the results come back. Of course, this vision is very nice. However, the main problem that we have always when training these artificial intelligences, which are often based on neural networks, is of course data. We need a lot of data to train neural networks. And for this problem, data is hard to come by because you have to recruit SQL experts. And the SQL experts, they usually what the process looks like is they have to come up with questions and write down also the corresponding SQL query. So the problem here is, of course, with this process is that it doesn't cover the whole range of data. Because what happens is that the annotators, they often just focus on the most prominent examples in the database. For example, in movie database, the most prominent examples are movies and actors. So questions around which actor played in which movies and so on. And the second problem, of course, with this is that it's super time and cost intensive. And the reason is, of course, if you have to come up with questions yourself and then write down the SQL queries, that takes a lot of time. And we can assume from other work that this process takes around 6 minutes per data point. And you also have to consider that with time, the mental strain on this annotator increases. So this also then makes the whole process more time intensive. In order to tackle these problems, we add two contributions. First, a new representation for the queries, and then second, based on that, a new annotation procedure. So let's take a look at the new representation first. We represent the queries as these operation trees, which are very closely related to the logical execution plans which you find in modern database technologies. So the idea is that, or the intuition behind them is that if you want to answer a question or a complex question, then this question is composed of many sub-questions. So for instance, here, this tree represents the question of what is the total runtime of all the family movies. So what we have here is all these tables that are involved in this query. We have the filter for filtering all the genres that are family. And then here at the end, we have the sum over all the runtimes. What you see here, in order to answer the question of summing up all the runtimes, we first have, of course, to answer the question or the sub-question, what are all the family movies, and so on. This representation has several advantages. So the first one is that it allows for more fine-grained annotation, which we'll see in a second. And it also allows for a better training material because it's it is more structured. So it's easier for it to be used as training material for neural networks. However, the biggest advantage that we exploit here during the annotation process is the fact that these trees are based on a context tree grammar. And it allows us to randomly sample these trees from this grammar and then solve the problem of not covering all the database content. Now let's look at the annotation process. The annotation procedure works in two phases. In the first phase, we randomly generate these operation trees from the grammar, and then we present these trees to the annotators, and the annotator's task is to write down the corresponding question to this tree. So their task now isn't to write or come up with questions, rather they have to first understand the operation tree, what it means, and then write down the question that this tree answers. So you have a couple of helpful tools, like if, for example, the filters or the constraints don't make sense, they can change them. And also they can look at the intermediate results of all these nodes in order to understand more what this query does. In the second phase, the annotators are presented with the tree and the question that has been written in the first phase from someone else. And in the first step here, they correct the question in case it was wrong. This is mainly to ensure quality. But then in the second step, they assign the tokens of the question to the nodes of the tree. So this is the fine-grained annotation that I was mentioning before. So this allows for these hard alignments between the tokens and the operation trees, which then can be leveraged during the training procedure. As you can see, this annotation procedures takes care of both problems that we looked at before. First, due to this random sampling of the trees, you cover or make sure that you cover more of the data in the database. And second, due to the fact that the annotators now only have to write the question given a tree, this reduces the time and cost intensity, because now people just have to understand the tree and write down the question and not come up with the question and write also the query. Now let's look at how our corpus compares to other corpora. Most notably the spider corpus, which is a corpus that contains pairs of natural language questions and SQL queries. They have been generated using SQL experts that have to come up with questions and the SQL query. And as you can see here, per query, they have like 6 minutes in order to come up with these queries. And we have like just around 100 seconds. So we are almost 4 times as fast doing this. Also, we don't have to recruit really SQL experts. We just have to recruit people that have an affinity to databases, so they sort of know what databases are and how they work, but they don't have to be experts. Then, as we can see here, the spider dataset has more databases because they had a different scope than we did. However, as you can see here, they have just 5.1 tables per database on average, and we have much larger tables in our dataset. And we also have a larger table coverage. Not only do we have more table per database, but we also cover more of these tables in our questions. And the same with attributes. We cover a lot more attributes than the spider corpus. The LC quad corpus is different. It's based on SparkQL, and also here we have a lot more coverage than they have. Then we look at the query complexity. Let's see how the complexity of the queries relate to other data sets. And also here we see that we have a lot more joins in our data set. And this is the strength of this representation with trees, because it allows easily to create or sample trees that have lots of joins in them. So we have more than 30% of our questions have at least 2 joins in them. Whereas in the spider data set, there are a lot less of these. We have fewer queries with group bys in them, and also fewer with set operations. However, we could tweak the random sampling process to create more of these. So this is just a question of tuning the sampling process. So we can control also how our data set should look like. So if we would decide that we want to have at least 40% of queries with group I, we would just sample accordingly. Of course, we also trained a neural network on our data. I won't go into the details about the specifics of the neural networks because I don't have enough time. So I will just show the score. So we classified the operation trees according to some hardness criteria. These are just heuristics based on how many operations there are and so on in the tree. And as you can see here, like the average overall score, the overall accuracy is around or almost 50%. So that means in almost like 45 to 50% of the cases, the neural network was able to create a tree that result, if executed against the database, corresponds to the result of the gold tree. As you can see here, most of the errors are made for the extra hard questions, and these are mostly those where you have group bys and set operations in them and lots of joins. So it makes sense that it doesn't work as well there. However, for the other ones, for the easy, medium, and hard questions, you get quite good scores. Except for the Formula 1 data set, which is very complex. You have to have lots of domain knowledge in order to solve this. So that's why the performance is significantly worse than for the other databases. Then we also looked at how these token assignments can be exploited. For this, we just added the tokens as in the attention mechanism of the neural network. We added a very naive way of including the tokens. However, already in this setting, the tokens, adding the tokens yielded like 2% increase in the scores. And we show this for different amounts of data used. So I can see here, if you just use 20% of the movie data trees to train it, we get a 7% bump just by adding the token information there. So as we can see here, the tokens already in a naive way to use them give a lot of score increase. So if we find out more interesting ways to implement them in our neural network, this score can even go higher. All right, that's it. So I will now be available for questions. Thank you very much for the attention.